compile time, which type gets returned. Meaning we can't use here the noise method, because the compiler can impossibly know at compile time, of course, which method he has to call. Is it this one or is it this one, right? And for that we will use dynamic dispatch. So again, we can put this in a box and using here the din keyword, meaning we want to go with dynamic dispatch here. And that means we have to box these instances. So now the return type over here is known at compile time, meaning we can annotate it. It would be a box which holds a type that implements the animal trait. And this is using dynamic dispatch, meaning we then can call this noise method on this instance here. Because the compiler can check for this noise method at runtime and not at compile time, meaning it is determined which of these will get called at runtime when the program is running. Let's see. And this is working. Trait bound. The impl trait syntax works for straightforward cases, but is actually syntax sugar for a longer form, which is called a trait bound. When working with generics, the type parameters often must use traits as bounds to stipulate what functionality a type implements. So over here we are calling the sum function with two arguments. In this case, two i32 arguments. And as you can see, we could also call this with floats because we have here defined the t generic type parameter. So as you notice, x and y must be of the same type t, and the type will be t which gets returned. And all we do over here is adding x plus y. Now again, to use this plus operator here, we must define that t over here is a type that implements the add trait. Because remember, this would actually translate to this. So it's critical that x implements the add trait, right? And we also have to define over here the associated type output to be of type t. Let's see. This is compiling. Let's actually call the function and print out the result. So as you can see, the output would be 10. And we can call it with floats, right? So let's see exercise 8, fix the errors. As you can see, we have a pair struct which has two fields holding values of type t, meaning they are generic. And then we have an implementation block for pair, and we define here an associated function. And this is not a method because it doesn't have self as parameter. Now over here we are instantiating a new pair. And remember, self over here, uppercase S, refers to the type of the implementation block, meaning pair. And then we return this instance. So if I write pair here, it would be the same thing. Then over here we have another implementation block for the type pair. And as you can see, we define here that T over here should implement the debug and partial OR. So the type T over here, the type of the two fields must implement debug and partial OR. Then over here we are defining a method compare display, which takes a reference to an instance of pair, and then checking over here, is the value of the X field bigger than or equal to the value of the Y field. If that is the case, then self.x will get printed out using debug notation. That is why we need T to implement the debug trait. Otherwise, we print out the value of the Y field. So as you can see over here, we have a custom type unit that holds an i32 integer. Now over here, we are instantiating a pair struct. And as you can see, we are passing here as concrete values for X and Y fields the unit type, our custom type. And over here it holds 1 and here 3, right? And i32. The type annotation for that would be, we would have a pair instance, and T over here would be unit, right? Because X and Y hold a type of unit. So T over here will be unit. Now remember, we have over here an associated function. So let's actually use that to instantiate a pair. As you can see, this is exactly the same thing as this, but here we are using the new associated function that got implemented on the pair type. So I can delete that. And again, when we call on this instance the compare display method, then we would have an error, because as for now, doesn't implement the debug and partial order traits. So we have to derive them. And by the way, we also need the partial EQ trait. And that's because we are here checking for equality. All right, so we need partial equality. And because we have now derived these traits for this type, it means unit implements debug, partial OR, and partial EQ, meaning we can over here compare for equality and ordering, and we can print the field out using debug notation. Let's see. And this is running. So the largest member is Y unit 2. So we have here a pair with an X field of unit 1 and a Y field of unit 2. And then the compare display method will give us back unit 2, right? Because the Y field holds a value that is bigger than the X field. Compare these two, because this is a custom type, is only possible because we have derived these traits. Alright, see you in the next topic. So before doing more exercises on trait objects, I want to cover associated types. Now an associated type allows to specify a type that is associated with the trait. When implementing the trait for a specific type, we have to specify the concrete type. It's basically a type placeholder that the trait methods can use in their signature. And it's similar to generic types, but they are more flexible because they allow a trait to have different associated types for different implementing types. Let's see an example. We have here the my trait, and this has an associated type called my type. And as you can see, we can then use this associated type over here in the methods we are defining in the trait. So we here, for example, define that the return type should be of type my type. Meaning when we implement this trait over here for a concrete type, like for example my struct, then we have to define the concrete type. As you can see, when we implement the my trait for my struct, we define here that my type should be I32. And as you can see, this method over here will then return an I32 type. And this is defined over here. And we can access the associated type using self, uppercase, double colon, and the name of the associated type. Now again, self here stands for the type we are implementing this trait for. So in this case, my struct. All right, let's do some more exercises practicing trait objects. As you can see, we have here a trait bird that has one method. Then we have here two custom types, duck and swan. So let's see, for duck we have an implementation block, and here we define a method. And this method takes a reference to the instance and prints out something. And for swan we also implement a method. Now notice, this has nothing to do with the trait. These are methods that are defined directly on the struct, right? So here we define a method fly, which again takes a reference to the instance and prints out something. Now over here we are implementing the bird trait for duck and swan, meaning we have to implement the method defined by the trait. So as you can see, this quack method we have to implement for both types. Then over here we want to instantiate a duck. So we then can call on this duck instance the swim method. So this will then get executed. Then over here we call the hatch a bird function with an argument of 2. And over here we call the hatch a bird function again with an argument of 1. So as you can see, when we provide 2, we want over here a duck. When we provide 1, we want over here a swan. And I see that because of the output when calling the quack method. So let's implement this function. We have seen that the function takes as an argument an integer. So let's call the argument species and let's define it as U8. Now I will keep the return type open. We will see that then. So let's see, when we get 1, let's actually match the species argument. When we get back 1, we want to return a swan. Right? If we get here for the argument a2, we want to return a duck instance. And because we have to handle all the cases, I will just panic in case anything else has been passed. So over here, what would be the return type? Now think about it. When calling this function over here, we have to provide the return type. Now, again, the return type has to be of known fixed size at compile time. Now, over here, we don't know what will get actually returned at compile time, right? Especially if this argument over here would be something that is generated at runtime, meaning we don't know the exact size, because this one struct could be larger in size than the duck struct or otherwise. So we have actually seen the solution. We need to box the return type, and we over here define that it should be dynamically dispatched, and that means we have to box these concrete values here. And now we are good to go, because also another problem would be that in a match, every return type has to be of the same type. Now again, over here, the function could sometimes return a swan or sometimes a duck, right? Depending on the argument. And when we do it like that, we actually return a type of box, right? So they have all the same return type. Now again, because we are here using dynamic dispatch, we have to put it behind a kind of pointer. And that means over here, we will get a box holding a trait object. And the trait object in this case is bird. So that means, and we have seen that the compiler will then allocate the concrete type, for example, over here, duck, in the heap memory, and will create a V table with all the methods. Because when we call over here the quack method on bird, then at this exact point, dynamic dispatch happens, because it is not known at compile time which concrete type got returned here. This will be determined at runtime. So at runtime, the compiler will check the V table and see the right, and will execute the right method call, right? In this case, it would be for duck. So the compiler will look this method up in the V table for the duck type, which has been allocated in heap memory. And we got, and notice something over here. When we return a trait object, the trait object actually only implements the methods from the trait, in this case bird, right? So we then can't call, because we have here a trait object, we can't call a method directly defined on the type. So for example, this swim method is not in the V table that the compiler creates. I hope you see that, because again, we are returning a trait object, meaning in the V table are only the methods from the trait. So over here, because we have created an instance on the concrete type, we can call the swim method. But over here, because we have a trait object, we can only call methods from the trait. Let's see. And as you can see, this is compiling. Array with trait objects. Again, we have the bird trait with the same method. Then we have duck and swan, And as you can see, these are methods that are implemented directly on the concrete type. Then over here, again, implementing the bird trait for duck and swan. We have seen that. Fill in the blank to make the code work. So over here, we want to have an array because we are here iterating over this bird's variable, meaning we want to iterate over an array. Now let's first annotate. We want over here an array of birds, right? So we want a type that implements the bird trait, meaning in this case duck and swan. And this time I will use a reference instead of a box. So we define over here that we want an array holding a type that implements the bird trait and is dynamically dispatched. All right. And again, because using dynamic dispatch requires that we put it behind some kind of pointer, either box or a reference. Now in this array, let's say we want to have two elements, one duck and one swan. So let's provide here the instances. And again, we have to put that behind a pointer so the size is known. So the size is known at compile time, because remember, the size of the elements in an array must be known at compile time. In this case, it would be usize, the size of a pointer. Now then we want over here to iterate over these elements here. And then, as you can see, for each element, we are calling on it the quack method. Now again, because this over here is happening at runtime, the quack method will be determined at runtime which one to run here, for duck or for swan. All right, let's see. And this is compiling now over, and here we have the same thing, bird.fly. The method we have directly implemented on the type isn't available, because in a trait object over here, only the methods from the actual trait bird are in the V table. Other methods won't get into the V table, and so the compiler cannot look it up at runtime. Referenced in and boxed in. So we have here a trait draw, which has one method, and we implement the draw trait for U8 and F64. As you can see, we can implement our own custom traits for types in the standard library. And all this does over here is it will take a reference of the instance and it will output the value. Now in the newer version of Rust, we don't have to dereference self here. This is happening automatically like that. And for F64, the same thing. Now, as you can see, we have here an F64 and an U8. Basically the types that implement this draw trait. Then over here we are calling the function draw with box. And as you can see, this function over here expects a trait object of the draw trait. And this trait object should be boxed. All right. And then it is calling the draw method. Again, the compiler will then look in the V table and will execute the appropriate method at runtime. So let's pass the argument for the draw with box function, and in this case we want to draw x, so let's pass it x. And of course this has to be boxed, right? Like this. Now over here we want to draw y, and this time we are passing a reference, meaning we over here expect a reference to a trait object that implements the draw trait. All right. And then we are calling the draw method again, this time on y. Let's see. And this is compiling. Let's see exercise 4. We have a trait foo, which has one method. Then we implement foo for U8 and string types. And as you can see, we can implement our own traits on types that are defined in the standard library. So in this case, U8 and string. Then over here in main, we have a variable x holding a U8 and y holding a string. Basically the types we are implementing foo for, right? And let's see now the function call static dispatch. So we pass here x, the U8 type, and this should be statically dispatched. So let's implement this function. Implement below with generics. So we need here a generic type parameter, and we define here a trait bound, meaning we want t to implement the foo trait, right? Because we want the argument to be of type t. So it's important that we define here the trait bound, because we call this function only with arguments that implement the foo trait. And we are defining that in order to be able to call the method on it. Basically this method defined here, right? Because then we can pass types of U8 and string to this function, and it can call the method because the foo trait is implemented for this type. Any other type that doesn't implement the foo trait won't be allowed to be passed to this function. So this is static dispatch, because the compiler at compile time will actually expand this code and create a function for the concrete types. So in this case, we are passing U8 to this function. So the compiler will create a function like this. Right? And then we'll call it. And this is happening at compile time, meaning the compiler will fill in the concrete types over here. And then of course the compiler will know when we do a method call which method over here it should call, right? And static dispatch is usually a lot faster than dynamic dispatch, because you don't have to do a lookup. It's everything in the binary itself. But when you have to do a lookup, you have to follow a pointer to heap memory and then get the data from this memory location, which is more expensive. So let's see dynamic dispatch in this case. And we use dynamic dispatch because sometimes it's just not possible to use static dispatch, right? When the size of the returned type cannot be known at compile time, then we use dynamic dispatch. And let's see how that looks like. So over here, we are passing a reference to y. So we are passing here a reference to a string. Now, as an argument over here, we want a reference, right? That's what we are passing to a trait object, implementing the foo trait, all right? And again, because this is dynamic dispatch, so this happens at runtime, it must be behind a pointer. So the size is known at compile time, because a pointer is always of size usize. We have covered that. And then we call the method on the argument, right? The difference is that over here, this will then be determined at runtime, which method over here to be called, right? Because the compiler will then do a lookup in the v table at runtime and then determine for which type the method should be called. Let's see. This is compiling. Object safe. You can only make object safe traits into trait objects. A trait is object safe if all the methods defined in the trait have the following properties. The return type isn't self and there are no generic type parameters. So let's see exercise 5. Use at least 2 approaches to make it work. Don't add, remove any code line. So I think we will go first with static dispatch because it's easier. So I will remove this box here. And let's see, we have a trait here defining one method. Now this defines that it takes a reference to a self, meaning a reference to an instance of my trait, and it returns self, where self over here refers to the type for which the my trait is implemented. So in this case, for example, over here, my trait is implemented for U32, meaning we implement this method over here, and self over here would refer to U32, right? We can write it either way. And U32 and string implement my trait. All right, so they both implement the f method. Then over here we have a function that takes a trait object. Now in this case we want to use static dispatch, so we define here a generic type, right? Because we are calling it with U32 and a string. Now we want to ensure that T, this type, implements my trait. So we can be sure that it implements this f method. So this is called trait bound, and this makes sure that T implements my trait. So we then can call the f method on the provided argument here, which is of type T. And that's basically it. We have implemented the static dispatch for this function over here. And what then will happen is when we call this function, the Rust compiler will take this generic function here and it will provide it with concrete types. And it will provide it with concrete types. So in this case, U32, right? We are passing it U32. And we forgot to define the return type. So the return type over here would be the return type of the f method. Now in this case, it would be the type, right? So if we are calling it, so if we are calling the f method on an U32, then the return type will be U32. If we call it on a string, then the return type will be string. So again, we pass here T, right? because the type we are passing, for example u32, will be the return type of this function u32, and that in case means that the return type of this function over here will be u32, right? And then the same thing happens for a string. So the compiler will actually put into these generic type parameters concrete types. And that means when we are using static dispatch, these method calls here are known at compile time. So the compiler knows if you're passing a u32 type, then it will call the f method from the u32 implementation of my trait, right? And in case of string, then the compiler will know that the f method can be found in the my trait implementation of string, right? So everything here is known at compile time, and also the size is fixed. And this is working. Now we want here to now use dynamic dispatch. So we solve it in two approaches. So before we can even use this trait object over here, we have to make the trait itself object safe. And we do that when the return type isn't self and there are no generic type parameters. So we cannot define here self. We have to provide it concrete types. Now in this case, we want the f method to return a trait object, meaning we return a pointer that points to the type that implements my trait. All right. And over here, because we are taking here this function signature and implement it for each type we implement the my trait for. So as you can see, the return type must implement the my trait, and it has to be boxed. So we have to box this over here. Turn over here a u32, right? Which implements the my trait, and over here a string. Which also implements my trait. So as you can see, we got rid of self, because again, at compile time, the return type size has to be known. That's why we are putting it behind a box. Now, again, the return type of this function would be the return type of the method calls. In this case, it would be a boxed trait object, right? Let's see if this is compiling. And this is also compiling. Now, I hope you see the difference here. When we pass here a trait object, basically a type, in this case u32, that implements the my trait, then this method call will be determined at runtime. And that's why we have to put these behind pointers, so the size remains fixed and known at compile time. And again, use whenever possible static dispatch because it's faster and I guess easier to write. But dynamic dispatch has its advantages and you can use it for more flexibility in your code. All right, see you in the next topic. So we have reached the topic of collection types, and string is also a collection type, meaning we are just repeating because we have covered strings, but I think these exercises are good for some repetitions. So string is a UTF-8 encoded growable string. It is the most common string type we used in daily development. It also has ownership over the string contents. So let's see, fill in the blanks and fix errors. Don't use toString, don't add, remove any code line. So as you can see over here, we want a string type because we are here modifying the string, meaning it has to be growable. So let's allocate this data over here on the heap. So we have now a string type. Now let's see the push stir method. As you can see, this push stir method is implemented on the string type, and it takes as a type for its argument a string literal. As you can see, we are calling it on a string and providing it an argument of a string literal. So we have to delete that because this would actually be a string, right? We want here a string literal, like that. And push is for pushing single characters. So we want to push here an exclamation mark. So S will then here match with this string literal. And as you can see, we are calling the move ownership function here, meaning this function will then take ownership of S, and that's not what we want because we are using here S again. So what we can do is just clone it. So the data passed to move ownership over here is actually cloned, right? It is copied on the heap memory. And that means we can still use S because S remains the owner of this data. All right. Then a string is stored as a vector of bytes but guaranteed to always be a valid UTF-8 sequence. String is heap allocated, growable, and not null terminated. A string slice is a slice, basically a slice to U8 integers, because as you can see, this string type is a vector of U8 integers. That always points to a valid UTF-8 sequence and can be used to view into a string, just like a slice to T is a view into vector T. And we'll cover vectors after this topic. So fill in the blanks. We have here a string, and we want to take a string slice from this string. Now the easiest method would be just to take a reference to S, which means we take a reference to a string type. And this can then be inferred by the compiler to a string slice. And the second way would be to call the sStir method on it. This will essentially do exactly the same thing. It will take this string S and will convert it to a string slice. Now over here, we also want a string slice, but we want to provide a specific offset. We just want this data over here. And that means we take a reference to S and provide it here an offset from 0. We can omit the 0 on here until index 0, 1, 2, 3, 4 until index 4. Now we would provide here 5 because 5 is excluded, meaning we go from index 0 to 4. And over here, as you can see, we want to modify the string, holding then hello world, because we are pushing to it this exclamation mark. As you can see, we want it hello world and with an exclamation mark. So what we can do is taking S over here as mutable reference. So this would then hold a mutable reference to a string. Let's see. And this is compiling. Now notice over here we could also take ownership of S, meaning slice 3 will hold a string because we are not using S after this point. So slice 3 can be the owner of S, but in this case we have to make the variable mutable. And this is also working. Question: how many heap allocations are happening here? So we have here a string, and when we create a string type, then the data that is provided is allocated in heap memory. So this would be the first allocation. Then over here we are taking from this string over here a reference, meaning a string slice. And remember, a string slice is just a view into some data. So we are just going to this location and checking what's in there. So no allocation is happening. And over here we are taking this string slice and convert it to a string, meaning a heap allocation is happening over here, right? Because we are taking this string slice holding this, and then we allocate this into the heap once more because we are calling this toString method. Let's see, indexing. So we have a string here and we want to index into the first element. So slice 1 should then hold age. So we want a string slice. So we take a reference to S and provided the offset from 0 to 1, where 1 is excluded, meaning we just take the first character. And that is because age only takes 1 byte in UTF-8 format. So ASCII characters in strings usually take 1 byte, while these Unicode characters over here take 3 bytes. So when we take a string slice here, we want to access this character. Now for that we have to provide the right offset. So we go from 0, 1, 2, 3, 4, 5, 6, 7, starting at index 7, and as you can see, these Unicode characters hold 3 bytes, meaning we must provide here an offset of 10. 10 is excluded, meaning we go from 7, 8, 9, 3 bytes. Iterate through all chars in S. So to iterate over characters in a string type, we use the chars method. But that will actually just return the char we are iterating over. But as you can see, we want here as return type a tuple which holds the index and the actual character. So we can use here the enumerate method. And enumerate will return a tuple with the index and the specific character. So in the first iteration we would have 0 and age, right? The index and the character. So here we are checking if the index over here is 7, then the variable c should hold this character, right? Let's see. And this is compiling. Now there is a crate called UTF-8 slice. You can import it into your project, and this then allows you to slice into a string, not using bytes as offsets, but just indexing into the individual characters. So over here we provide an offset from 4 to 5, meaning we want the character at index 4. So we don't have to worry about the byte size of this symbol. Then fill in the blanks, we have here a string. Now we have seen that a string is actually a vector holding U8 integers. And as you can see, we have here some bytes in a vector. So this vector holds U8 integers, right? And that means these are bytes that can be converted to ASCII characters. So in this case, these over here would translate to hello, all right? If you look up this code over here in the ASCII table, then we will find that this is represented for the character H, and this ELLO. So we want to turn a bytes vector like this into a string. So we want a string here. So let's see this method here. So in the documentation, you can see that the string type implements a method from UTF-8. And this just takes a vector of bytes, and then we can call this associated function on the string type and provide it as an argument a vector of bytes. And this will then convert it to a string. So we can try it out. So first of all, we want to actually mutate the string here to hold the same data as this vector holds, namely hello. So we can do that by using push stir. And we push hello, meaning this string then holds hello. And then we can take this string type and call from UTF-8 method, providing it this vector. And this should then convert this vector of bytes into an actual string, meaning S and S1 will then hold the same value, namely a string hello. And of course, this actually returns a result, so we have to unwrap it. And as you can see, this is compiling. So in fact, a string is just a vector of bytes, right? And we'll cover vectors very soon, and you will then see how this is actually stored in memory. So a string is made up of three components: a pointer to some bytes, a length, and a capacity. The pointer points to an internal buffer string uses to store its data. The length is the number of bytes currently stored in the buffer, always stored on the heap. And the capacity is the size of the buffer in bytes. As such, the length will always be less than or equal to the capacity. We have seen that the string type is a three-word object holding a pointer to the actual data stored in heap memory, the length, which shows the length of the string, in this case 5, and the capacity. And the capacity, as you can see here, is the total amount of memory received from the allocator. So when we allocate a new string type on the heap, the allocator will find an empty spot and then will return a pointer to that location. So, number 6, if a string has enough capacity, adding elements to it will not reallocate. So when we run this program over here, then we see the capacity of string S. Now over here we are initializing an empty string, meaning we have an empty string, so nothing gets allocated to heap memory. we still have a string object, but with a length of 0 and a capacity of 0. Then we print it out, as you can see, 0. Over here, we are iterating 2 times, modifying this string. So in the first iteration, s will then hold hello. So it would have a length of 5, but when we print out the capacity, it will show 8. So we have a string object that points to this data with a length of 5 and a capacity of 8. Now this is the default behavior when we don't specify a capacity ourselves. So when the length exceeds the capacity, then Rust has to reallocate the data, meaning it has to find a new spot in heap memory that is big enough to hold the data, and then will return a pointer to the new location. So in this case, because we have modified the string, the length 5 exceeds the capacity 0. So it has to reallocate, because remember, in heap memory, the data is allocated as contiguous block of bytes. All right. And the default behavior is that the capacity will always double. So it starts from 1, then 2, 4, 8, 16, and so on. And that's the reason we have here a capacity of 8, even though we only need 5, right? This is a string of length 5. But because of the default behavior of the allocator, we will get back a capacity of 8. And then in the second iteration, we again push hello, right? So we would have a length of 10. But as you can see, the capacity doubles. So 10 exceeds the length of 8, meaning the allocator will then find a new spot in heap memory to allocate this string over here of length 10, and it will then reserve 16 bytes of memory in heap memory, and so on. If we then exceed 16 bytes, then it will allocate to a location which holds 32, right? It always doubles. And this is when you let Rust allocate. So this is the default behavior. But as you can see, this might be expensive. So if you start with a capacity of 0 and then you modify the string multiple times, it means Rust has to reallocate your data. And that means it could potentially be expensive when you mutate this over here multiple times and a lot of reallocations are happening. So there is a function called with capacity. And then we can define over here that we want an empty string, meaning the string length is 0, but we want a capacity of 25, meaning S is allocated in heap memory and there is enough space reserved for this data to hold 25 elements, right? So when we do that again, then as you can see, no reallocation has happened. We have only allocated the string one time in heap memory with a capacity of 25. Now, because the length doesn't exceed the capacity in any of these modifications of the string, it means that there is no need to reallocate the data, right? So when we print out the string S over here in the end, then as you can see, this is the string that S holds in the end, hello, hello. So we have here 10 elements, meaning there is no need for reallocation because a capacity of 25 can hold the string of this size, and this can make your program a lot faster. So let's see vectors. A vector is like an array but dynamically sized, meaning they can grow and shrink. It's allocated on the heap as contiguous block of memory. All elements in a vector have to have the same type. And there is a special macro vec which you can use to initialize a new vector. So all this time we've been dealing with an imposter. So in actuality, this string type is just a vector of UTF-8 bytes that gets allocated in heap memory. So as you can see, when we have the S1 variable over here, then again, S1 won't hold the actual data, but a pointer to the data allocated in heap memory alongside a length and a capacity, meaning S1 is a 3-word object of size 24 bytes. Now, as you can see, this would be a vector allocated in heap memory that holds the UTF-8 bytes over here. Of course, in memory, this would be in binary, but as you can see, this then holds the character code for this character inside the string. So let's do some exercises. Vectors are resizable arrays. Like slices, their size is not known at compile time, but they can grow or shrink at any time. So over here we have a normal array holding 3 U8 elements. Now we can convert this array to a vector using the from associated function and then passing it the array, meaning V will then hold a vector of U8 elements. And here you can see the difference between an array and a vector. We don't provide here the length of the vector because the vector can actually grow or shrink, meaning it's dynamic in its size. Now the isVec function basically just checks if the provided argument is a vector. Then, as you can see, we are shadowing V and we are here initializing it with a vector of these elements. So as you can see, you can use the vec macro to quickly create a new vector like that. So this will then hold a vector of U8 elements. And by the way, you can either use square brackets or you can use parentheses. It's both exactly the same. Now, as you can see, here we are initializing V, or basically shadowing it, and then we are passing it to isVec, meaning ownership would be transferred. But we are using V here again, so let's clone this. And over here, as you can see, we are initializing V1 with the vec macro. Now we are passing to the vec macro the array. Now the vec macro over here won't convert it directly to a vector like this from associated function did. Instead, we would here have a vector holding this array. All right. I hope you can see the difference. Here we have a vector of U8 elements. Over here we have a vector holding an array of 3 U8 elements. So when we compare over here V and V1, they won't actually be the same, right? And again, let's do clone here, just so we can then reuse V1. Now what we can do over here to fix that is using the vec new, like that. And vec new basically will then create a new empty vector, meaning it would be an object with length of 0 and capacity of 0. Now over here we want to iterate over the elements in V. Let's take a reference here because we are using V again and we don't want this for loop to take ownership. Now all we want to do is pushing all the elements from V into V1. And because we are here iterating over references of elements, we have to dereference it. And by the way, we will take a look at that in much greater detail. So what we also have to do is making this v1 variable mutable, because when pushing to it, it has to be mutable. All right, let's see. And this is compiling. So in the end, v1 will hold a vector of u8 elements, meaning v and v1 are exactly the same. But remember, when you have an array, use the from associated function and not the vec macro, because it won't convert it directly to a vector. Instead, it will create a vector holding an array. A vec can be extended with extend method. So over here we have a vector. Let's say these are i32 values. And as you can see, we can pop, meaning removing the last element. So over here, the vector will then hold 1 and 2 because the last element got popped. Then we are pushing to it 3. Meaning we have a vector holding 1, 2, 3. Now over here again we are initializing an empty vector. Now as you can see, we want v1 and v2 to be exactly the same. So what we can do is using the extend method and providing it the v1 vector, meaning the elements and we have to pass here a reference, meaning the elements then from v1 will be put into v2. So again, v2 will then be a vector of i32 elements and they hold exactly the same data, right? It's basically copying the contents of a vector into another vector. Turn x into vec, fill in the blanks. So over here we have an array. And this array holds i32 types and the size of the array would be 3. Then as we've seen, we can use the from associated function. So we create a vector from this array, meaning v1 will then hold a vector of i32 types. Or what we also could do is calling the into method. And if a type implements from, then it will implement into, and we will take a look at that. So we then take this array over here and convert it into a vector of i32 values, right? So that means v1 and v2 will be exactly the same. Now converting a string into a vector. So the from trait over here is actually implemented for the vector type. So over here we have a string, and remember, basically a string is a vector of u8 elements. And then again we can call here into, right? Converting s into a vector of u8 elements. And then over here we have again a string, and we call the method into bytes, meaning v2 holds a vector of UTF-8 bytes, represented as u8. And this is actually exactly the same, so meaning v1 and v2 will be identical. Then over here we have a string literal, and we want to create a vector from this variable, meaning we again use the from associated function and provide it as an argument over here, meaning v3 will then hold a vector of u8 types, right? So v2 over here and v3 are identical. Iterators can be collected into vectors. So when we have here an array of 10 elements of value 0 and we put it into an iterator, we can then collect it into a vector. Alright, and we will see these methods over here, intuiter and collect, in much greater detail. Meaning v4 will then hold a vector of 10 times 0. Like that. Alright, let's see. And this is compiling. Fix the error and implement the code. So let's see, over here we have an array and we convert this array into a vector using the from associated function we have seen. So this will then hold a vector of i32 types. All right. Now then we are iterating here 5 times and just print out each element at the specific index. Here we have to implement some code, and actually v in the end should hold a vector with these elements. So as you can see, we are starting with a vector holding 1, 2, 3, and we end with a vector 2, 3, 4, 5, 6. Now what we want to achieve here is we are adding 1 to each element, then we would have 2, 3, and 4. Now if we exceed the boundary over here, then we want actually to add the new element over here. Now let's see first in the for loop here, this would actually panic because we are trying to access indexes that are out of bounds. So over here we are iterating from 0 to 4, right? 5 excluded, but we have only 3 elements, meaning indexes 0 to 2. Now we can here use the get method, and we have seen this get method before, and this is generally safer because it will return an option. In this case option i32, because we are dealing with i32 types here. And what we then can do over here, we want to actually manipulate this vector. So let's first access the elements. And as you can see, again, I use the get method because we want to actually see if the index is out of bounds or not. So in case it's not out of bounds, we would return a sum, right? The get method will return a sum and the actual value at that specific index. So if we found an element at the specific index over here, then we want to access the element and just add to it 1, right? So we are then taking the element over here. Let's see, for example, in the first iteration, I will be 0. Then we pass 0 to this get method, meaning we will get back some 1, right? So we'll get back some 1, meaning E over here will then hold a value of 1. Then we access this array at index 0, right? And what we want then to do is taking 1, E over here, and add to it 1, meaning then the first element in this vector has been modified to then hold 2. Now in the second iteration, it would be exactly the same thing. So I would be 1. We get over here the element at index 1, and E will then hold 2. And then over here, V at index 1 should then hold 2 plus 1, right? And we assign it, meaning in the modified vector, the second element will then hold 3. Now we do that again, and after we are out of boundaries, meaning we return a none here, and then we want to push to the vector the index plus 2, right? So for example, in the third iteration, I would be 3, right? This would be out of bounds. There is no index 3 here. So we get back a none. And then over here, we push to V the index, in this case 3, plus 2, meaning we then get back 5, right? And let's see if this is actually working. All right, and let's remove this type annotation because this would be of type usize because of the get method. Now, as you can see, when we print out here the output of the get method, we would get some 1, some 2, and some 3, and then 2 times none, because at iteration 3 and 4, we would get back none because there is no element in this index. And we are succeeding here because, again, we have 3 times sum here, and when we have a sum, we just add 1 to the value, meaning we then have 2, 3, and 4. And then we will get back 2 times none, meaning we take the index and increment it by 2, pushing it to the vector. So we get 5 and 6. Slicing. A vec can be mutable. On the other hand, slices are read-only objects. To get a slice, use reference. In Rust, it's more common to pass slices as arguments rather than vectors when you just want to provide read access. The same goes for string and string slices. So over here we have a vector, let's say I32. Then we are taking a slice from V over here, meaning this would then be a slice of I32 elements, right? And this would be the offset, meaning we would take from the first element to the last element. Out of bounds will cause a panic. You must use V length here. So as you can see, again, we are taking a string slice, but we are here out of bounds, right? Because this would iterate from 0 to 3, 4 excluded, and we have here only 0, 1, 2 indexes. So what we can do is using v.length, meaning we just iterate, meaning we provide an offset from 0, the first element, to v length, where the length here is excluded, meaning v length minus 1. All right. Slices are read-only. Node slice and reference to vec are different. So as you can see, we take here a mutable reference to a vector. And then we can push to this vector over here the value 4. Now we have seen that slices are immutable. They are just a view into some data. So we can't use a slice to mutate the vector, right? So over here we want to have a slice of I32 elements, right? Like that. And we can remove the mute keyword over here because again we can't modify slices. So we have pushed to it 4, meaning when we take the slice we want to take also this last pushed element, right? And this is compiling. Capacity. The capacity of a vector is the amount of space allocated for any future elements that will be added onto the vector. This is not to be confused with the length of a vector, which specifies the number of actual elements within the vector. If a vector's length exceeds its capacity will automatically be increased, but its elements will have to be reallocated. For example, a vector with capacity 10 and length 0 would be an empty vector with space for 10 more elements. Pushing 10 or fewer elements onto the vector will not change its capacity or cause reallocation to occur. However, if the vector's length is increased to 11, it will have to reallocate, which can be slow. For this reason, it is recommended to use the with capacity function whenever possible to specify how big the vector is expected to get. And this we have already covered with strings, but now let's see with vectors. So over here, as you can see, we are initializing an empty vector, but with a capacity of 10. So this object here would hold length of 0 and capacity of 10, meaning the actual elements inside vector are 0. There are no elements, but in heap memory, there were 10 locations allocated for this data, right? The vector contains no items even though it has a capacity for more. So when we call the length method over here, we would get back 0, right? Because vec doesn't hold any values. But it has a capacity of 10 because we have defined that over here. These are all done without reallocating. So we are then pushing 10 times to the vector. Right? Now this means vec here holds enough space that this is happening without reallocating the vector, right? So after pushing to the vector would be of length 10 and capacity 10, right? So the length must never exceed the capacity, otherwise a reallocation is happening, as we can see here, but this may make the vector reallocate. So we are pushing another element to the vector, meaning the length will be 11. This would exceed the capacity, meaning then this whole vector will be reallocated in heap memory. So when we have a length of 11, then the capacity will be at least 11, but it can be more, because we have seen that the default behavior when reallocating is that the capacity doubles. Fill in an appropriate value to make the 4 done without reallocating. So as you can see, we have here a vector we want to initialize with a certain capacity. Then we are pushing 100 times to this vector, meaning the length here will be 100. So what we want to do is we want here to initialize a vector with a capacity of 100, meaning we can push 100 times without this vector to be reallocated in heap memory. Store distinct types in vector. The elements in a vector must be the same type. For example, the code below will cause an error. So we have here integers and a float. This would cause an error because, again, all of them have to be of the same type. But we can use enums or trait objects to store distinct types. So over here we again see the IP address enum we have seen before in the examples. Now fill in the blank. We want over here a vector that holds IP addresses, meaning at index 0 we want this variant here, and at index 1 we want this variant. Now we can use the vec macro for that. And then over here I just copy this variant and this over here, right? We would then have over here a vector holding types of IP address. And because this is a custom type, we have to actually implement partial EQ here. So I hope you get the concept. We have here a vector holding types of IP address, right? Then over here we have a trait IP address that defines one method display. And then we have two tuple structs, v4 and v6. We implement the IP address trait for v2 struct and v6 struct, meaning we have to implement this specific method. And all it does, it then basically prints out the value that is stored inside the struct. So fill in the blank. As you can see, we want here a vector holding trait objects. Remember, a trait object is boxed or put behind a reference. So over here we have a vector holding boxes, right? And the box holds a trait object, meaning, again, this is using dynamic dispatch, and we want here a type that implements the IP address trait, right? In this case, v4 and v6 both are types that implement IP address. And as you can see, even though we are holding here different types, we can use it using here trait objects to store it in the same vector. Typo. So, and then we are iterating over the vector, and for each element in here we just call the display method that has to be implemented, because we only have types in here that implement the IP address trait. And this is exactly where dynamic dispatch happens, and we have covered that. Let's take a look at hash maps. So a hash map is a data structure to store key value pairs. It's allocated on the heap as it is dynamically sized, meaning it can grow and shrink. It allows for efficient lookup, insertion, and deletion of data. So when talking about time complexity, this means accessing and modifying elements, or entries as they are called in hash maps, would be in the best case at constant time, meaning big O of 1. While in the worst case, if you have a lot of collisions, then it would be still linear time, which is still pretty fast, which means big O of n. Each key is hashed to a unique index in the underlying array. So, where vector stores values by an integer index, hash maps store values by key. It is a hash map implemented with quadratic probing and SIMD lookup. By default, a hash map uses a hashing algorithm selected to provide resistance against hash DOS attacks. So over here we find some information about the used algorithm for the hash maps. But let's dive into the exercises. So the first thing is we actually have to use here a namespace. So we are basically importing from the collections module from the standard library the hash map type. And when using vectors or strings, these are all in the prelude, meaning we don't have to import it, but a hash map you have to basically import. So over here we are initializing an empty hash map. Then we insert some entries, and again a hash map holds entries of keys and values. Now important here is that all the keys must be of the same type and all of the values must be of the same type. So this over here would cause an error. And let's go with integers like that. And we annotate the hash map like this, where key stands for key and V stands for value. So over here we use string literals as keys and I32 integers as values. Then, as you can see, we can access the entries in a hash map by using again the get method, which returns an option. We have seen that before when dealing with vectors. So we provide the get method the name of the key, all right? And then we will get back the appropriate value, in this case 98, because we are accessing the entry sun phase, right? So we would get back here a sum, an option I32, right? This would be the return value, sum 98, and this would be the type, option I32. So we can check if the hash map contains a certain key. So for example, if the hash map contains the key Daniel, this would evaluate to true, meaning the code block here will be executed. And we can also index into a hash map using bracket notation like that. So again, this would then hold the value of the entry Daniel, it would be 95, right? And this would be an I32. Again, notice the difference between indexing like that or indexing using the get method. We will get back the value here directly, while here we get back an option. So get is generally safer. And then over here we are removing Daniel from the hash map, right? So we can use the remove method and provide it the key of the entry we want to delete. Meaning after deleting Daniel over here, the length of the hash map would be 3, right? And we can also iterate over a hash map. So we provide it here, the variable holding the hash map, and then the return would be a tuple holding the key and the value. And then we just print out the key and the value. Let's see. All right, and we would get back here an option holding a reference to I32. All right. And over here too, we would get back a reference. This is what the get method will actually return. So as you can see, we are printing out the hash map. And this would be the key, for example, Ashley, and this would be the value, as you can see. Now notice that the order here is different from what is over there. And that's because a hash map is unordered. So the order won't be retained, all right? And of course, we have only 3 elements here because we have removed the entry of Daniel. Then over here we have an array holding tuples, which holds a string literal and an integer, right? So we have an array of 3 elements, and each element is of type tuple, and inside the tuple is a string literal and an I32. Then over here we are initializing a new empty hash map. Then we iterate over here through the elements of this teams array. So for each element here, we insert into this empty hash map here the name over here, the string, and the value. All right. Implement team map2 in 2 ways. Tips: one of the approaches is to use collect method. So we can also implement a hash map from an array holding tuples of keys and values by using the hash map from function. So we provided here teams, and this will then directly convert this array holding tuples of keys and value pairs to a hash map. Meaning we then have a hash map holding string slice keys and I32 values. All right. And over here we would have the same thing. And then when we compare teams map 1 and teams map 2, they should be equal. Let's see. This is compiling. Now the second approach would be taking this teams array here, and we want to put it into an iterator. And again, we will cover that. And then we call collect. Now, when we call the collect method, it will basically collect the elements in this iterator into the type we have annotated here. Again, this would compile because we have in teams map 2 the same keys and values as we have in teams map 1. And as you can see, we don't need to write a full-blown for loop. We can just use some simple methods. Let's see, number 3, fill in the blanks. So type inference lets us omit an explicit type signature, which would be hash map, string slice, and U8 in this example. So again, we don't have to annotate the types. I do it just to make things more clear, but we can leave it at that. Insert a key only if it doesn't already exist. So here we are accessing player stats, this empty hash map, and we call the entry. Now the entry checks if an entry exists with this specific key. And then we can call over here the OR insert method, meaning if this entry doesn't exist, then we insert this key with this value. Meaning when we then access player stats with a key of health, we should get back 100, right? Because this has been inserted over here. Insert a key using a function that provides a new value only if it doesn't already exist. So again, we are trying to access player stats and look for an entry health. Now in this case, this exists, right? Because we have inserted it at that point. Now we can also use here the method OR insert with. The difference to OR insert is that we don't provide a concrete value, but a function pointer, meaning this function will then get executed. So this function only returns 42. So that means if the entry health doesn't exist, we insert this key with the value of 42. Now again, health exists, meaning when we access health, we will still get 100, right? Because this only executes if entry isn't found. Ensures a value is in the entry by inserting the default if empty and returns a mutable reference to the value in the entry. So we are here checking for the entry health, and if it doesn't exist, we insert 50, right? So in this case, health already exists, meaning we would get back a mutable reference to the existing value 100, right? So this would be a mutable reference to 100. And because it is mutable, we can then modify the entry manually. So we can here decrement from health, which holds 100, we decrement 50, meaning the health will then hold 50, right? This health variable holds 50. Let's see. And this would be U8 in this case. And this is compiling. So as you can see, when we call entry, it will give us back a mutable reference to the value. If it already exists, to the existing value. If it doesn't exist, it will here create an entry, because this is what the OR insert method does, and will return a mutable reference to the created value. And then we can modify this mutable reference, right? Requirements of hash map key. Any type that implements the EQ and hash traits can be a key in hash map. This includes bool, int, uint, string, and string slices. Note that F32 and F64 do not implement hash, likely because floating point precision errors would make using them as hash map keys horribly error prone. All collection classes implement EQ and hash if their contained type also respectively implements EQ and hash. For example, a vec holding a type T will implement hash if T implements hash. So if the elements in a collection, for example a vector or a tuple or an array, implement the hash trait, then the collection itself will implement hash. Let's see, fix the errors. Tips derive is usually a good way to implement some common use traits. as you can see, we have here a struct Viking with two fields of type string. And here we have an associate function for Viking, just creating a new Viking instance from the arguments we provide. And as you can see, use a hash map to store the Viking's health points. So we are creating here a hash map from an array holding tuples of keys and values. Now notice we have here a hash map, and the type of the keys would be the custom type Viking, all right? And the value would be I32. Use derived implementation to print the status of the Vikings. So here we are taking this created hash map as a reference, and we would get back a tuple holding the key and the value, and then we just print out the key and the value here. So we have seen that in order a type can be used as a key in a hash map, it has to implement EQ and hash. So let's implement that. Let's also use the partially Q over here and debug, so we can print out the key over here in debug notation. Let's see. And of course we have to implement the hash trait. And as you can see, it will print out each element in the hash map we have created. So we have now a hash map using as key our custom type Viking. As you can see, this would be the key and this would be the value of the hash map. Capacity. Like vectors, hash maps are growable, but hash maps can also shrink themselves when they have excess space. You can create a hash map with a certain capacity using hash map with capacity, or use hash map new to get a hash map with a default initial capacity. This is recommended. So like we did with strings and vectors, we can define when initializing an empty hash map the capacity, right? Ensuring that when we know we will push a lot of entries, that there are no reallocations, because remember, reallocations are slower. So then we are here inserting two entries. And as you can see, this would be an entry of key I32 and value I32. So the key and the value can be of the same type. And over here we insert again another entry. Indeed, the capacity of hash map is not 100, so we can't compare the equality here. So even though we have here defined that the capacity should be 100, it could actually be more than 100, and this is just in case there are collisions, there are some internal stuff going on. So the Rust compiler will actually allocate more capacity than 100 we defined here. Shrinks the capacity of the map with a lower limit. So when we call map over here, our hash map holding two entries, and then we can shrink the capacity to 50, right? So again, the capacity won't probably be exactly 50 then, but around 50. So we can shrink the hash map and shrinks the capacity of the map as much as possible. So because over here we have only a hash map of two entries, 50 spaces in heap memory would actually be more than we need. So we can use the shrink to fit method so that the capacity will shrink around the amount of elements it actually holds. Again, it won't probably be 2 exactly, but around this number. Ownership for types that implement the copy trait, like I32, the values are copied into hash map. For owned values like string, the values will be moved and hash map will be the owner of those values. Fix the errors with least changes, don't remove any code line. So over here we have initialized a variable with a type of I32 and an empty hash map, right? Then we insert here an entry into M1 and using the same exact value for the key and the value, meaning we have here a hash map with keys of type I32 and values of type I32. Over here we have a string and we initialize here an empty hash map. Then over here we are inserting a new entry using v2, the string here, as the key and v1 over here as value. So we would have here a hash map using of keys of type string and value of type I32. And because this is an owned type, meaning it doesn't implement copy, this will then actually be moved into the hash map. So we can't use v2 here. But what we could do to fix that is we could use a string slice of this string, right? We just provide a reference, meaning then the hash map will have type for the keys of string slices, right? And that means we can then again use v2. And again, because v1 is of type I32, it means it implements the copy trait, meaning even if we pass it as a key in the hash map or as a value, it is still usable. But when you are dealing with types that don't implement copy, the ownership will get moved, meaning hash map will then be the owner of the type. Alright, and there are some third-party hash libs, but I won't cover that in this beginner's course. So see you in the next topic. Let's now look at type coercion, and we have already seen the as keyword, and this is mostly used for converting integers. So type conversion, also called typecasting, is coercing a primitive type that can be performed by as keyword. As conversions can be chained, and when casting to an unsigned type t, for example, then t max plus 1 is added or subtracted until the value fits into the new type. And using unsafe methods can lead to undefined behavior. So let's see an example. As you can see, we have here the largest unsigned 8-bit integer, 255. And this would be the binary representation. This means that U8, right, this data type for unsigned 8-bit integers, max, meaning 255, plus 1 will be 256. So for example, if we typecast 1000 as U8, then let's see what the compiler will do. It will subtract 256, this value over here, from 1000. And then it will check 744 is still bigger than the largest value it can represent, meaning it will do the same thing. Subtracting 256 will leave us with 488, still bigger than this value. So again, the same thing, it will subtract 256, and this will leave us with 232, meaning this will then be the returned value when we cast 1000 as U8. Because remember, an 8-bit unsigned integer can't represent 1000, it's out of bounds. Now, when we typecast -1 as U8, then remember, an unsigned integer cannot represent negative numbers, meaning what it will then do, it will basically rotate. So 0 would be the smallest possible number an 8-bit unsigned integer can represent, and then -1 will just basically rotate. It will go back to the biggest one, meaning this typecasting over here will result in 255. So convert by as. Rust provides no implicit type conversion coercion between primitive types, but explicit type conversions can be performed using the as keyword. Fix the errors and fill in the blank. Don't remove any code. So over here we have an F32 float, right? Then we typecast this float into an U8, meaning over here the fractional part will get removed. So the value would be 97. And of course this will then hold a U8. Now we want to typecast this decimal into a char. Now this is not possible directly, but we have seen that we can chain as statements. So we can convert this first to an U8, meaning we will get 97 like we did here, and then typecast it to a character. So C1 will then hold a character. And by the way, 97 would be the ASCII code for A. And over here, as you can see, we can typecast this integer holding an U8 type as char directly. So C2 would also hold a char. Now, as you can see, we are here comparing the integer holding 97 with this typecasting. Now, this typecasting over here converts the B character to its U8 representation. Now B would be represented as 98. So what we can do over here is adding 1 to 97, because remember 97 would be A. Meaning when we add 1 to it, we will get back B, right? So both of them will hold 98. By default, overflow will cause compile errors, but we can add a global annotation to suppress these errors. So, as you can see, the largest possible number U8 can represent would be 255, meaning this would cause an error. Because again, 1000 is larger than the largest possible number a U8 can represent, meaning we have here an overflow error. Now we can actually allow overflowing by using this attribute. So this then won't complain, right? And then when we print out V, as you can see, we would get back 232, because we have seen over here that this would be the result when the compiler performs this operation. So we allow here overflowing literals. right? If we comment this out, then the compiler will complain because this is actually not possible. When casting any value to an unsigned type t, t max plus 1 is added or subtracted until the value fits into the new type. That's what we have seen. So in this case, 1000 as U16 would return 1000, right? Because a U16 can represent a number of 1000. But over here, we would have an overflow, meaning this would return 232, like we have seen over here. For positive numbers, this is the same as the modulus. So this would actually be the same as doing 1000 modulus 256. Remember, U8 max plus 1, meaning 256. Now, we have also seen in the example when we have -1 and casting that to an unsigned integer, it will then basically just rotate. So this will return 255. Since Rust 1.45, the as keyword performs a saturating cast when casting from float to int. If the floating point value exceeds the upper bound or is less than the lower bound, the returned value will be equal to the bound crossed. So in this case, we have a float here, casting it to U8, meaning a saturating cast will be performed. So it will just return the largest possible number U8 can represent, which would be 255. Now, in case we have here a -100 as floating point and convert it to U8, this just would return 0, the smallest possible number U8 can represent. This behavior incurs a small runtime cost and can be avoided with unsafe methods. However, the results might be overflow and return unsound values. Use these methods wisely. We can use here in an unsafe block the method toInt unchecked. So the compiler here won't actually check what's going on. So as you can see, we are casting 300 floating point to an uint to a U8. So as you can see, we are here casting 300.0 floating point to an U8 integer, and this won't be checked by the compiler. That's because it's in an unsafe block. Now this would return 44, right? Because 300 minus U8 max plus 1 would be 300 minus 256, meaning we would be left with 44. And -100 as U8, as you can see, we are typecasting this floating point to an U8 integer. And again, this is unchecked. So again, what the compiler will do here, it will take U8 max plus 1, meaning 256, and it subtracts 100, meaning we would get 156. And not a number would be converted to 0, okay? And of course, here we have to use again the attribute allow overflowing literals, just so this will actually compile, because usually this won't compile. And as you can see, this would be the output. Now over here we are dealing with raw pointers, and we won't cover that in this beginner's course because this is more of an advanced topic. So see you in the next topic. So we have seen type conversions for integers and types from the standard library. But what if we want to convert types that we defined, basically custom types? And Rust has for this the from and the into trait. So let's see, from and into traits are used for type conversions between different types without requiring explicit casts. It's part of the standard library and can be implemented for custom types. Implementing the from trait for a type will give us the into implementation for the given type for free. Meaning when we implement from, we implement it into automatically. So always implement the from trait and not the into trait. Let's see here an example. We have a custom type number. And then over here, we are implementing the from trait, right? So we want to convert from an I32 to our custom type number, right? And the from trait implements a method from. So we take here as an argument an I32, and we will then create a new instance of the number type with the provided value and then return it. And that means when we use here the from associated function on our custom type number and provide it an I32, then this can directly be converted to our custom type, right? And we can do it in two ways, from, as we've seen, because we have implemented it. And I've told you that when you implement the from trait, the into trait is automatically implemented, meaning we can also call the into method on the type we want to convert to. But when you use into, a type annotation is needed, so the compiler knows into what type you want to convert this type, right? So we convert here a type of I32 into a number, and this would be the implementation. So the from trait allows for a type to define how to create itself from another type, hence providing a very simple mechanism for converting between several types. The from and into traits are inherently linked, and this is actually part of its implementation. It means if we write something like this, so we implement here the from trait for the custom type u, then we can use u from t, right? We can then create a u type from the type t. We have implemented the from trait on. Or we could also use into, so we convert t into u. The into trait is simply the reciprocal of the from trait. That is, if you have implemented the from trait for your type, then the into trait will be automatically implemented for the same type. Using the into trait will typically require the type annotations, as the compiler is unable to determine this most of the time. So for example, we can easily convert a string slice into a string. As you can see, we have over here a string slice, and then we can call string and the from associated function, providing it this string literal, meaning this will then be converted to a string. And we could also use the toString method. Again, this and this is exactly the same. And we could also then use the into, because remember, when we implement from, we get into for free. So we convert this myString string literal into a string. And again, type annotations are needed. Because the standard library has already implemented this for us, impl from string slice for string. So we can easily convert a string to a string slice and vice versa. Some implementations of from can be found here. So as you can see, we have here impl from bool for i32, meaning we can convert a boolean into an i32. So when we have here a boolean value and call into, it will convert this boolean value into an i32 integer. In this case, this would be 0, 0 for false and 1 for true. And again, when we can use the into method, we can use the from associated function. So we call the associated function on the type i32 and provide it here the boolean value, right? So this will then actually be exactly the same. Fix the error in two ways. First, implement from char for. Maybe you should check the docs mentioned above to find the answer. Second, a keyword from the last chapter. So let's see the docs. So we want here to convert a character. So let's see over here, as you can see all the types that implement the from trait. So we want to go from character, and as you can see, we can convert a character to either U32, U64 or U128 as well as string. So I32 is not supported. And as you notice, these are only unsigned types because it's logical. A character can't be negative, right? It can't hold a negative number. So we only have unsigned integers here. So we can then in fact convert a char into a U32, let's say. So in this case, char implements. So in this case, we use here U32, right? We can convert from a char to a U32. Meaning when we change this over here, this should actually work. So we provide here a character called the into method, and then we should have an U32. Fix the error in two ways. So we can't use the as keyword here. This is not implemented, but what we can do is let's first use the from method. So we can create a string, or basically converting a character into a string, because we have seen in the documentation this is actually implemented. And the second way would be to call a and then into, right? Like we did over here. Implement from for custom types. From is now included in standard prelude, so there is no need to introduce it into the current scope. So we don't have to import the from trait. It's actually in the prelude, meaning we can use it without importing anything. So over here we have a custom type number with one field. Now we want to implement the from trait for our custom number, meaning we should be able to convert from an I32 into a number. So when we call over here number from, right, then we should get over here number. This would then create an instance of the number struct. And the value field here will hold a value of 30, right? So, and the same thing is when we would call 30 like that and call into, right? This should then convert the I32 integer into the number type automatically. And remember, we only have to implement the from trait because then we can use from and into both of them. So let's see. So this over here is the from trait. And let's take this function signature over here and copy it like that. Now in this case, self refers to number, right? And what we want to do is create here a new instance. And we just take the value, in this case, the I32, right? And we provide it as a value for the value field. And again, because the name of this argument matches the name of the field, we can use it like that. And this is sufficient. So let's see. And this is compiling. So as you can see, then it's really easy to convert one type to a custom type we have created. When performing error handling, it is often useful to implement from trait for our own error type. Then we can use question mark to automatically convert the underlying error type to our own type. Now, we didn't cover that. This will be the next topic, but let's see the exercise. We have here an enum CLI error. Now, the two variants here, IO error and parse error, hold error types from the standard library. Okay? And these are actually the error types that get returned in case of an error when using these specific methods that are implemented in this standard library. So as you can see, we want here to implement the from trait for different error kinds from this standard library, and we want to convert that to our custom error type, CLI error. So let's see, over here we have the function open and parse file. It takes a file name as argument and it returns a result, and we will cover results. So a result basically says in case of success, it will return a result with I32 and otherwise CLI error. So then we call the read to string function, and as you can see, this is defined in the fs module. Fs is used for file manipulation, and we provide to this function over here the file name. Now we pass a reference because this is defined in the documentation of this function. We are here using the question mark operator, meaning in case of success, the result type that will get returned will be unwrapped and contents will hold a string. In case of an error, it will return the CLI error, meaning the rest of this code won't get executed and we just get a CLI error instead. Now, the error type returned from this function would be IO error. So in order this error to be converted to a CLI error, we have to implement for this error type the from trait, right? But let's see what's happening here. We then take the contents, meaning this string over here that gets returned in case this function call is successful. And we then hold over here the contents of the provided file. Then we trim and then we parse. Now parse could potentially fail. And parsing is basically converting a string to an integer value, right? So in case of success, we will get out an I32. In case of error, we will get back a num parse int error. This is defined in the num module. Again, we will cover error handling and all of that. Don't worry. This is now just about the type conversion. And then we return an OK with the num value here. We have to wrap it in OK because we return a result type. Now let's see how we would implement that. So again, I will just go to the documentation and copy the function signature like that. So we have the function signature, and then we can over here see what we want to do. So in case we get an IO error, we want to convert that to our custom CLI error. Now, how would we do that? Let's change here the argument to E for error, and the type would be IO error, right? We are implementing it from this type. Now what we want to do is we just want basically to pass the IO error into the IO error variant in our custom type. So we can access the variant. So we can create an instance. Remember, this is the syntax to access the enum. So we access CLI error and then the IO error variant. And all we do then is just passing this IO error type, meaning we then have an instance of this variant holding our IO error. And that means we have then implemented the from trait for our custom type. So any IO error type can be implicitly converted to CLI error, meaning in case this function over here returns an IO error, it will implicitly be converted to a CLI error. Let's do the same thing over here for parse int error. This would be the error type from the parse method. So again, let's change here the argument name, and the type would be over here. And then we again just access this enum. We want to access the parse int error variant, and we pass it the actual error that gets returned. And this would mean we then create another instance of the parse error variant. Let's see if this works. And as you can see, this is compiling, meaning in case of an error over here, both these error types from the standard library, IO error and parse int error, will be implicitly converted to CLI error, right? Try from, try into, similar to from and into, try from and try into are generic traits for converting between types. Unlike from into, try from and try into are used for fallible conversions and return a result instead of a plain value. Now again, we use the result type, we will cover that when there is a possibility of an error, of something going wrong. So as you can see, we have here an I16 holding 256. IntoTrade has a method into, hence try into has a method try into, right? This is the method defined on the try into trade. So we take this value here and call the try into method on it, meaning this will return a result. So we match this result. In case of an OK, then we unwrap the value from the result. And if it is an error, then we just print out the error over here and return 0, right? So in case this succeeds, then n will hold a U8 and the value. In case this fails, n will hold a value of 0. Now we have seen that when we want to convert an U8, then this would actually fail because this is out of boundaries. But because we are here basically error handling, that means that the program here won't actually panic. So in case this fails here, which it does, then we will just assign to n the value 0 and print out the error. So in this case, n would be 0. And again, error handling will be our next topic. So don't worry if this seems a little bit strange. Then over here we have a tuple struct even num, and it takes an I32 type. We implement here the try from trade for the custom even num type. Now here we have an associated type and we define that it should be of type unit type, okay? And then we implement here the try from function. So all this function basically does, it takes a value and it checks if it is divisible by 0, and then we will return the result, in this case okay, even num, and inside it the value provided. Otherwise, if it is not divisible by 2, then we return an error holding our unit type we have defined here. As you can see, the type in case of an error would be this associated type error, meaning a unit type. So we have provided that over here. So then we can use the try from function. So when we call even num and try from 8, then this would return okay, right? Because 8 is divisible by 2. So we would get back a result, in this case okay, even num, and the value we have passed, right? That's what we defined here. Now in case we try from a value of 5, this would return an error with a unit type inside, because again 5 is not divisible by 2. Now with try from and try into, it's exactly the same like with from and into. When we implement try from, then try into is automatically implemented. So we can use this try into method here directly. So we try here to convert 8 into this result, right? And the result in case of success will hold the type of even num and otherwise a unit type, like defined over here. And in this case, result will then hold okay, even num, and the value we have passed, 8. Now when we call try into on 5, then this will actually return error and a unit type inside, like we have defined over here. Let's see. And this is compiling. See you in the next topic. Let's now see two more exercises, and this time we are converting a custom type into a string. So to convert any type to string, you can simply use the toString trait for that type. Rather than doing that directly, you should implement the fmt display trait, which will automatically provide toString and also allows you to print the type with print line. So again, same thing like with from and into. If you implement from, then into is for free. So you usually don't implement this trait directly for a type. You implement display and you will get toString implementation for free. So let's see. We import here fmt and we have here our custom type point. Now here we are instantiating a point. So what we want to achieve here is that when we take the point instance here, we have instantiated and converted to a string. This should then be the output. And we can also use the format macro here. Basically just providing origin, because the format macro will automatically convert that to a string in order to print it out, and the output will be the same. So let's implement the display trait here. So as you can see, this is the display trait and it provides one method. Now let's take it from over here. They provide here an example. And we can just copy this over here. Now I remove the lifetime, it's not needed. And let's implement the fmt method here. So as you can see, the fmt method provides here a formatter, meaning we want to write, we can use the write macro here, and the write macro works like println or format, but the difference is it will write to a buffer, in this case f. This is the formatter from the fmt module. And then we here provide what we want to print out. So in this case, we want to print out the point is and the values. So let's do that. And then, like in a println macro, we provided the values. So in this case, we want self.x and self.y. We want to print out the x and the y field. And that's basically it. We have implemented the display trait for point, meaning our customly created type point can be converted directly to a string. So let's see. And this is compiling. So if we pass origin here, let's see the output. As you can see, this would be the output. So we can even manipulate how the output should look like. So instead of just printing out the two fields, we have even provided the output with a whole sentence, right? This will be the last one we will be doing. We can use parse method to convert a string into an i32 number. This is because from string is implemented for i32 type in standard library. To use from string method, you need to introduce this trait into the current scope. So we have to import this trait from the stir module. So over here we want to parse, and parsing again means converting a string into an integer. So we would here have an i32 type of this value, and over here the same thing. Now we can either annotate the type over here, or we could use the turbofish syntax, meaning we can directly annotate the type on the method like that. And then, because the from string trait is actually implemented for the i32 type, we can also call the associated function from stir. Let's do 20 here. So this will convert from this string literal into an i32, meaning this will then hold an i32. Now, because all of them hold i32 integers, we can then do a mathematical operation, meaning we just add together all of these values, 5, 10, and 20. So the variable will hold an i32, and it should be equal to 35. And this is compiling. See you in the next topic. Now we will cover error handling, and the simplest form of error handling is to use the panic macro. Panic will print out an error message, unwind the stack, and finally exit the program. Now, unwinding the stack means that when you actually execute the program, then we have seen that the local variables and the function calls will be pushed to the stack. Now, when panicking, that means that the compiler will actually delete everything step by step from the stack memory and then exit the program. And in multi-threaded programs, it will exit the thread in which the panic occurs, not the whole program. So we don't deal here with multi-threaded programs. This will be another course, but I just want to mention it. So let's see exercises. As you can see, we have here a function drink, which takes a string literal. If the string literal is lemonade, then we print out success. Otherwise, we actually want to panic, right? Because we want to ensure that this line never gets reached, meaning never gets printed out. So when we pass over here lemonade, then this will print out success and then will panic. And this would be the output if a program panics. Thread main panicked at explicit panic, and it will provide you the line number at which the panic occurred. In this case, an explicit panic, because we have here called the panic macro. Common panic cases. Make the code work by fixing all panics. So when we call here the asBytes method on a string, then it will give us back the array holding the UTF-8 bytes of this string. Now we have seen that actually the UTF-8 representation of A would be 97, B would be 98, and C would be 99. So again, if assert EQ doesn't match, if this does evaluate to another value than this, then assert EQ will cause a panic. Over here we have a vector, and we try here to access the third index. Now we only can go to index 2, right? It's the outmost index we can provide. So let's change that. And this will then hold an i32, right? Because we are accessing a specific element. Unwrap may panic when get return a none. So the get method over here will return an option, meaning it either returns a sum with a value or a none. Now in this case, this would return a none because we don't have any value at index 3. So when we try to unwrap a non value, then we will panic. Now let's here access index 1, for example. Then it will return a sum 2, right? The first element, right? The element at index 1. And unwrap will basically just unwrap the inner value. So LA will then hold a value of 2 of type I32. Sometimes the compiler is unable to find the overflow errors for you in compile time, so a panic will occur. So when we call here the production rate per hour function with a value of 2, then let's see. We have here speed, the provided argument of type U8. And here we have CPH of type U8. Now, as you can see, we are inside here multiplying the speed, in this case 2, by CPH 222. Now this would actually result in an overflow because 2 times 221 would be 442, right? Now remember, an U8 can only represent up to the number 255. So this would actually cause a panic. But what we can do is just actually taking here a U16 and converting that to U16, meaning when we multiply these together, then the result of U16 will still be able to represent the resultant number. And over here we can do the same thing. And then let's see, because of the same reason as above, we have to wrap it in a function to make the panic occur. So here we are calling the divide function with two arguments, 15 and 0. So the divide function takes two arguments of type U8 and just divides it. Now this would also panic because we can't divide by 0. This is a mathematical rule and this will always lead to a panic. So let's here divide by 1, for example. Let's see if this is compiling. Alright, and again, when we use the get method, we will get back a reference to the value and not the actual value. So let's change that. And this is compiling. Detailed call stack. By default, the stack unwinding will only give something like this. So this would be the output if your program panicked. Though there is the reason of panic and the line of code is showing where the panic has occurred, sometimes we want to get more info about the call stack. Fill in the blank to display the whole call stack. Tips: you can find the clue in the default panic info. So when we run cargo run, this is basically how you execute a program you have written, and we'll cover that. Then you just provide over here this rust backtrace equals 1 environment variable, and it will then give you detailed information about the panic that occurred. So over here, unwinding and abort. By default, when a panic occurs, the program starts unwinding, which means Rust walks back up the stack and cleans up the data from each function it encounters. But this walk back and cleanup is a lot of work. The alternative is to immediately abort the program without cleaning up. If in your project you need to make the resulting binary as small as possible, you can switch from unwinding to aborting by adding below content to cargo.toml. So we can here define in this cargo.toml file, and I will show you an example of that, how panic actually behaves. So we have two options here, either unwinding or aborting. When choosing abort here, then the stack won't get unwinded, meaning this will then be the responsibility of the operating system and not of the Rust compiler. Alright, see you in the next episode. So we have seen the option type, and the option type stands for a value that could potentially be absent. So let's now look at the result type. Result is an enum type that represents the outcome of an operation that could potentially fail. It has two possible variants: OK, a value t was found, and error, an error was found with a value e. And as you can see, the variants hold the specific information. The expected outcome is OK, the unexpected outcome is error. Since result is an enum, the possible variants can be matched using a match pattern, and that is what we call error handling. So let's see an example. Let's again consider the divide function we have seen before. So again, we can't divide by 0, meaning if the second argument here is a 0, then we should return an error. Otherwise, the program will panic. Now we can do here error handling, meaning we check if y is 0, right? Or in this case 0.0, because the arguments are floating point numbers. Now in case y holds a value of 0, then we return the error variant of the result enum, and we provided an error message. All right. So in this case, we use an explicit return keyword, meaning when this returns, it won't execute any further. It will directly return the error type and stop execution. Now in case y is not 0, then we will just divide x by y and wrap it inside OK, because remember, result is an enum, meaning we have to wrap the resultant value inside the variant. So that means when this function succeeds, then we will get back an F32, right? The result of this operation. And this is wrapped inside OK, because as you can see, we are returning a result type. Now in case of an error, we would return this string over here, wrapped in the error variant. And this allows us then, when we call the function divide with two arguments, that we can then match the result we get back here. As you can see, we would get back a result type, meaning the result type has two variants, either OK or error. And we can here use pattern matching to destructure the inner value, for example, this F32, into the variable val, which we then can print out. And in case of an error, we will get back this string over here, the error message. And we destructure it into this variable here and then print it out. Unwrap. The unwrap method takes as input a value of type result and takes out the value which is wrapped inside OK in case of success, or panics in case of an error. In case it returns an OK variant, we just take the value that is wrapped inside. Otherwise, the program will panic. So you should use unwrap only if you're 100% sure that the return variant will be OK. Otherwise, you should use match. And let's see the question mark operator. The question mark operator is a shorthand way to propagate errors or unwrap OK results. Basically, it's the same as unwrap, but instead of panic, it returns an error. It replaces an entire match statement and it can even be used in the main function. So as you can see over here in the main function, we can define here that main should return a result type. And as you can see, we have here a string holding a number. Then we try to parse this string over here into an I32 type. Now we have seen that the parse method could potentially fail, right? If we have here a string holding T, for example, the compiler can't convert it to an I32 because it's not a valid number. So in case we get back the OK variant, remember parse will return a result. If we get back OK, then we just take the inner value and return it, meaning the inner value will then be assigned to the number variable. In case of an error, we want to return, meaning this over here won't get executed, it will return before. And we just provide the error message over here. And in this case, because we are using a function from the standard library, this error message is actually provided, right? So we just take the provided error message and return it. And if this didn't fail, it means this will get executed, and we just print out the unwrapped number. Now, because we return here a result type, we have to also return an OK in case everything succeeded. Now, because at the end of main, basically the end of the program has been reached, so it doesn't make sense to return any meaningful value. So we just return a unit type like that. So I've told you that the question mark operator actually replaces an entire match statement, meaning this over here would be exactly the same. So let's see. Again, we are in main and we return a result. Now, as you can see, we have again a string holding a number. Then we try to parse over here, and again parse returns a result, so we have to handle the error case. Now we can do that appending to it the question mark operator, meaning in case this succeeds and it returns an OK with the value, in this case 10, but parsed as an integer, then it will just assign it to this variable, meaning number will then hold 10 as an I32. In case this fails, then it will return a parse int error as defined in the parse method. Okay, so this over here is exactly the same like we did over here. And when this returns an error, the following lines won't be executed. In case this succeeds, then we have number which holds 10 of type I32. Then we'll just print out the parsed number, and then we return a unit type, because remember we are here returning a result, meaning we have to also return OK variant in case of success. But again, because we are in main and this would be the end of the program, we don't return any meaningful value, we return a unit type. And there is also a concept called type alias. So it's basically just a way giving a name to an existing type. So if you like to write use64 like this, then you can create a type alias, meaning we can use the type keyword and provide a new name for a specific type. And as you can see over here, we are then using the new type we have created here. And this would at compile time then be replaced with the real type. And please don't confuse that with associated types in traits. They are different, okay? Let's see. Result is an enum to describe possible errors. It has two variants, OK and error. In short words, the expected outcome is OK, while the unexpected outcome is error. So let's see, fill in the blanks and fix the errors. First of all, we are importing the parseInt error from the num module, because we are using here the parse method, meaning it will, in case of an error, return the parseInt error. Now we have here the function multiply that takes two arguments of type string literals. Okay. Now, as you can see, we are here returning OK, meaning the return type will be of type result. And in case of success, or let's actually wait with annotating that, let's first see what's happening here. So we are taking this string literal and try to parse it to an I32, right? So again, this parse method over here will return a result. In case of success, we would have OK and the value that was parsed. So for example, when we call here multiply with an argument of 10 for the first parameter, then we would have a parsed number 10, right? So we would have, in case of success, an I32 here. In case of an error, we would have the parseInt error, like that. And parseInt error is the error type that is defined for this method. Again, this is implemented in the standard library, so this has to comply with what is defined there. And N2 is exactly the same, but for the second argument. Then over here, we unwrap, and remember, unwrap will take a result and just unwraps the inner value. So in case we have OK, let's take the first argument 10. Then unwrap will just unwrap the inner value, meaning it returns the integer I32, right? That is wrapped inside the result enum. And then over here, we are multiplying by N2. Again, we have to unwrap because this is a result type. And if this succeeds actually, then we will return an OK, meaning OK will then hold in this case 10 times 2 will be 20, right? Like that. So we return an I32 in case of success. In case of error, we will return a parseInt error, because that is the error that is defined from the parse method. So let's see, when we call multiply with these two string literals 10 and 2, then this should actually work, right? Because the compiler is able to parse these into integers. So it will parse here, and this will then be OK 10, and over here we would have OK 2. Then we unwrap both of these over here, meaning we unwrap the value from the variant, and here 2, meaning we multiply 10 by 2. And then this would be 20, and we wrap it inside OK, because we have to return a variant of the result enum, which means that the return type over here would be this, right? So result in case of success will hold OK and 20, right? Now in this case, this would actually fail because the compiler can't convert t to an integer. Now we want this to actually assert to 8, so let's do here 4. And this means this will get parsed to 4 and this will get parsed to 2, right? And then again, we just multiply these together and return it wrapped inside the OK variant. Meaning over here, we get back a result, and result will then hold OK and 8. Right? Now, if we unwrap the result over here, then it would unwrap the inner value. As you can see. So unwrap method allows us to unwrap the inner value. So OK 8 would be unwrapped to 8. Question mark operator is almost exactly equivalent to unwrap, but question mark operator returns instead of panic on error. So let's see, we have again the parseInt error. Implement multiply with question mark. Don't use unwrap here. So let's see. Again, we are taking two arguments of type string literal, right? 3 and 4 in this case. And let's start to implement. So we declare here n1 and we take n1 string and try to parse it into an I32, right? Now again, we should here use the question mark operator. So we append it after the method call here, and then we can only use the question mark operator when the return type of the function is a result, right? Because the question mark operator, in case of an error, will return the error variant and inside it the error value. So we return here a result. In case of success, it should be I32. And in case of failure, it should be this parseInt error, because again, this is defined as the error return value of the parse method. Now for n2, we do exactly the same. And that means if any of these fail, then it will immediately return, meaning the rest of the function won't get executed and a parseInt error will be returned. Now the question mark operator, in case of success, it won't return a result, it will unwrap. So for example, when we pass here 3 and this will get parsed, it will return OK and 3, right? And then the question mark operator, like unwrap, will unwrap the inner value. So n1 will then hold 3, meaning an I32 integer. And n2 the same thing. And then all we want to do is just returning an OK in case of success, because the return type is result. And we want to multiply n1 by n2. Notice over here that I didn't have to unwrap, because we have here I32 types, right? While over here we had to unwrap because these held result types. You have to remember that. Let's see. And of course I have to change that over here, typo, and this is compiling. So what we had over here when we provide 4 as a string, we would have OK 4, right? And then the question mark operator unwraps the value. And then over here we are multiplying 3 by 4, which would be 12. And then we wrap it inside OK to comply with the function signature. So this will then be the returned value, right? And then over here, as you can see, we are calling the function and unwrap it because we have here a result type. So we unwrap the inner value because this would return OK12, and we unwrap it, meaning the inner value gets unwrapped. Let's see over here, we have the file type from the FS module, and over here we are importing some stuff from the IO module. So over here we are opening a file, providing here to the open associated function the name of the file in form of a string literal, meaning this will then return a result, and in case of success it will hold a file, right? And in case of error it would be IO error. All right. And then we are matching F. Now F holds a result, meaning we must over here handle both cases in case of success and in case of failure. So if it is okay, then we unwrap the inner value, meaning the file, and we just assign it to F. In case of an error, we return the error wrapped inside the error variant of the result type, right? Because this function over here returns a result. All right. And then over here we are creating a new empty string. We then take F over here and read to string, meaning the contents of this file over here will be copied to this string, meaning S will then hold basically the contents of the file we have opened. And we have to provide here a mutable reference because this is defined in the standard library. And then again, because this read to string method returns a result, we have to match it. So in case of OK, then we will return over here a string, right? This string S over here. In case of error, we will return the error. And both of them, file open and read to string, return an IO error. All right. Now over here, fill in the blanks with one code line. Don't change any code lines. As you can see, we have here the function read file to, which returns a result. In case of success, it's a string. In case of error, it will be the IO error from this standard library. We here declare a new string, and we here initialize a new empty string. And I told you that the question mark operator replaces a whole match statement. So we can write all of this in one single line. So first of all, we are opening the file. So let's take this. And as we've seen, open will return a result. So we can use the question mark operator here to replace this whole match statement. So in case of error, it will immediately return, and it returns this error type. In case of success, then we will get OK and a string, and this will then unwrap it to this string, right? And in case of success, we will have a value of type file, like we saw over here. And again, file is a type defined in FS module. So we have seen that the question mark operator will then unwrap. We will basically get something like that, and it will unwrap the file inside the OK variant. What we then can do is call the read to string method on it, right? So we are calling read to string, and then again we have to append this question mark operator, because read to string also returns a result type, right? So in case of success, we'll then over here mutate s, meaning the contents of this file will get read to this string, all right, or written to this string. And then we just return s, right, this string. And that means in case of success, we will have as return type a result that is holding a string. In case this or this fails, then it will return an IO error. Meaning if this fails, then over here a IO error gets returned and this will never be executed. And if this fails, again, we return this error and this will never get executed. Let's see. This is compiling. Map and then. Map and then are two common combinators for result TE, also for option T. So we have over here the parse int error, fill in the blank in two ways, map and then. So we have here the function add2, taking a string literal and returning a result. In case of success, holding an I32. In case of error, parse int error. All right, because this is the default error type of the parse method. Then we are taking this string literal and try to parse it to an I32. And then, as you can see, when we provide here add2 with a string holding 4, then we want to get back 6. So as you can see, when we provide 4, we will get back 6 over here. And that means we want to parse this string and then add 2 to the parsed number. And for that, we can use map, which is really convenient, because we not only want to handle this result case, but also then modify the value, right? So n here takes a closure, and we will cover closures very soon. So we provide here an argument n, and n would then hold the parsed number. And all we do is adding 2 to n, right? And that's all. So let's actually see the map method in the documentation. As you can see, maps a result TE to result UE by applying a function to a contained OK value, leaving an error value untouched. So when we call the map over here, it will it will apply a function if this method returns an OK value. If it returns an error, then it will leave it untouched. All right. So in this case, this would actually succeed, right? So parse over here will parse this 4 into an I32 integer, meaning it will then take the OK value and unwrap it, so n will then hold a 4, and then we just add n, and then we just add 2 to 4, right? Let's see. And this compiles. Now the second approach would be using and then. Now and then is very similar to map. The difference is here in the closure that the and then method takes. So let's go back to map here. So over here you can see this is the argument for the closure, right? And the closure over here returns directly the value, all right? And over here the closure itself will return a result. Now both of these methods return results over here, but the difference is in the closure, and you will see what I mean when we are looking at this. So this is very similar. It will take this parsed integer and then put the unwrapped value into n. And then over here we add 2 to n. Now we have seen that map would work like that, and then method will actually return in the closure itself a result. So we have to wrap that into OK, like that. But otherwise they are exactly the same. And this succeeds. Number 5, with the return type rewritten, we can use pattern matching without unwrap, but it's so verbose. So here again we have the multiply function taking two string literals. In case of success, it returns an I32, otherwise parse int error. So over here we are using the match keyword. Now we want to parse the first string literal, the first argument. In case of OK, then we destructure it into the variable n1. So n1 will then hold the parsed number. In case of an error, we just return the error type. Then we match inside this match arm over here again. So we match the second argument, parsing it, and if this is okay, then we get out n2, all right? And then we can multiply n1 by n2 and return the result wrapped in the OK variant. Because as you can see, the function returns a result type. And in case of an error, it just returns an error. So this would be very verbose. So rewriting multiply to make it succinct. You should use both and then and map here. So let's see. We take first of all the n1 stir over here, the first string literal. All right. Then we want to parse it to an I32 integer, right? And let's then use and then. So if this succeeds, then we will have here n, which holds the parsed integer, right? And let's actually write it more beautiful like that. So we take then n, or let's call it n1, just to make a distinction. And then over here we want to parse the second one. Right, we want here the second one. And then if this also succeeds, we want to multiply n1 and the parsed n2 together. So let's use map here. And we would here have n2, right? Because map over here is called upon the parse method. So we would then get back n2. And then we just return n1 times n2. And notice, because we are using map here, we don't have to wrap it inside OK, right? So this will then return, for example, when we call it by 10 and 2, it will return 20. All right? And then we have seen that it will return the result type. So in case of success, it will return OK with an I32 value inside. Otherwise, it will return a parse int error. Let's see. And this is compiling. So as you can see, when we are calling the multiply function with 10 and 2 as string literals, it will parse the first argument, meaning we then have over here OK 10, right? And then over here we call the and then method. All right, so we take this n1 value here, basically unwrapping it, and inside and then we parse the second number. So in this case 2, right? So this will then get parsed into an I32, and we then can map, meaning we have n2 over here, and 2 in this case would be OK 2, right? And map will take and unwrap the value inside OK, meaning we then have n2, which holds 2 over here, and then we multiply n1 by n2 and return it. All right. And all we then do is here the returned value would be of this type, right? And in this case, this would return OK 20, right? Because it could parse these two numbers and it multiplied it and returned it. So we get OK 20. Then we pass that to the print function. As you can see, it takes as an argument a result type. Then we match it. If it is OK, then we print out the value wrapped inside OK, in this case 20. Otherwise, we will print out the error. And when we call multiply with an argument that can't be parsed, then we would get a parse int error, right? So this would then hold a parse int error. We are providing that to the print function, and then we match the argument, this tt, and this will then match the error, meaning the error will get printed. So in the first print call, n is 20, so we have successfully parsed these two numbers and unwrapped the value, printing it. And in the second one, because we provide here an argument that can't be parsed, we get an parse int error, and this would be the error message that is provided in this standard library. So type alias, using this type over here everywhere is verbose and tedious. We can use alias for this purpose. So at a module level, creating aliases can be particularly helpful. Errors found in a specific module often has the same error type. So a single alias can succinctly define all associated results. This is so useful, even the standard library even supplies one, IO result. So as you can see, we have here again the parse int error, and we want here to create a type alias. Now we have here the same multiply function we have seen above, so I won't cover that anymore, but the return type is defined as res I32. And the print function over here takes as an argument a type of res I32. Now, as you can see, exactly the same functions as we had over here. but we don't write out the whole type. We use here a type alias. So we can define that here. We use res i32, and we want to define that as a result. In case of success, holding an i32. In case of an error, as you can see, the parse method would return a parse int error. And then instead of writing that all the time in our functions, we can use this simple type alias. And of course, at compile time, these type aliases will then get replaced with this concrete type here. Let's see. And as you can see, the same output as before. Using result in fn main, typically the main function will look like this. However, main is also able to have a return type of result. If an error occurs within the main function, it will return an error code and print a debug representation of the error, debug trait. The following example shows such a scenario. So as you can see, we have here again the parseInt error, and we define here in the main function that the return type should be of type result. In success, returning a unit type. In case of error, it will return a parseInt error. So over here we have a string literal, and we are then trying to parse this string literal to an i32. Now again, parse returns a result, so we have to handle both cases. In case of OK, we just take the wrapped value and assign it to a number, right? In this case, this would hold an i32. In case of an error, it will just return the error, and it will stop execution from this point. And then all we do is we will print out the number. So let's see if this is compiling. And as you can see, this is compiling. We are printing out the number. And don't forget, because we return a result type here, we have to return the result variant OK with a unit type in case of success. We provide here a unit type to the OK variant because the end of main means the end of the program. Because the end of main means the end of the program. So we don't have to actually return anything here, right? Because if the program ends, this returned value won't be beneficial. But we can just provide the unit type so we comply with the function signature. And by the way, as we've seen, we can here just use the question mark operator. So we can replace this match statement by this. And this is actually the reason most people use here in main the result type, because then it allows us that we use the question mark operator. Otherwise, if we didn't have result here, we can't use this operator. Let's see. Of course, I have to remove the match keyword here. And as you can see, this would be the same thing. All right, see you in the next topic. Let's take a look at Cargo. Now, Cargo is the official package manager and building tool in Rust. It helps automate tasks such as creating new projects, building, running, testing code, and managing dependencies. A crate is a compilation unit of Rust source code. So basically a crate is the smallest amount of code the Rust compilers considers at a time. And crates.io is the repository for Rust packages. So as you can see, this is the website of crates.io, and here you find some libraries. For example, we have here the rand library, and this allows for creating random numbers. And as you can see, you can add this very quickly into your own project, and we'll see how this will work. What is a crate? A crate can be of two types. Either it's a binary crate, and that means the program is compiled into an executable binary. It's basically a program you can run. And binary crates always have the main function in it. And a